Today we will derive the expression for the intensity of an electric dipole in a simple and clear way. It is a very important topic for class 12 exam. Before we go any further, let's explore a few curiosities that frequently pop up in our mind, such as number one is, what does intensity actually means? And number two is, what happens when two charges equal in magnitude but opposite in nature come together? And the number third is, what is the influence of the direction on the electric field intensity? After watching this video, you will know everything about these curiosities. So stay with me until the end of this video for all of this. So hello everyone, namaskar and greetings to all of you and welcome to my channel Derivation. We are going to dive into a very important topic, electric field intensity. Before deriving the expression, it is essential to know a few important concepts of the intensity with the help of two main points. And what are those two main points? The two main points will be written on this whiteboard, such as number one, intensity in the context of the brightness. And the number two is intensity in the context of the pressure. Let's move on to our first point. When you light up your bulb, your eyes sense some brightness, and as well as you move a little closer towards the bulb, your eyes sense even more brightness. What does that show? That shows that as we keep moving towards the bulb, the brightness keeps increasing, and this increasing brightness is what we call intensity. Now let's move on to our second point. When you hit a nail with your hammer, you feel some pressure on the nail, and again with a harder blow, you feel even more pressure. What does this show? This shows that as we are increasing the blows of the hammer on the nail, the pressure keeps increasing, and this increasing pressure is also itself is intensity. Similarly, other example can also be given, but out of consideration for time, that's all for now. Now let's move on to our main topic. And what is our main topic? Our main topic is to drive the expression for the intensity of an electric dipole. So it is our main topic. But before driving its derivation, first of all, we write its heading. And the heading is intensity at a point of an electric dipole on the axial line. So it is our heading. After this, we will write its definition. And the definition is electric field intensity is the net intensity at a specific point in the electric field of a dipole, and it is equal to the vector sum of the intensities due to each charge of the dipole. After writing this definition, we will understand its meaning. So for this, first of all, look at this definition and read it carefully. So we see that after reading this definition, we will find that there are two questions that arise. And what are those two questions? The two questions are as follows. Number one, what is the meaning of this definition? Number two is, what is this definition trying to say? So this definition is trying to say that when we place a test charge in an electric field of a dipole, such as let Q naught is a test charge, and this field two intensities, number one is E1 and number two is E2. Due to these two intensities, there will act a net intensities on this test charge, and that will maybe as a direction from left to right like this. So after understanding this definition, we will place this dipole like this, in a dielectric medium, and this dielectric medium has a dielectric constant capital K. After placing this dipole in a dielectric medium, we will draw its figure. It is a rough figure, but we will draw a neat and clean figure that satisfy all the condition of this definition. So let's start drawing the figure. First of all, we draw a line and mark 3 points on it, such as two of them are at the extreme point and the third is at the center of this line, and names these points as A, O, B, because we know that O is at the center. So the distance between OA and OB will be same, and we call it as L. So this distance will become equal. Now we place minus Q charge at point A and plus Q charge at point B. You have to pay attention to one thing. What has this become? And what you are now seeing is a system. So the combination of different quantities in this figure has become a system. And you know that the system which has two charges equal in magnitude and having an extremely small distance ranges from micro to nano or even small is a dipole. And you know that every dipole has a dipole moment, and this dipole moment acts at the center of the dipole in direction pointing from minus u to plus us, and it is represented by vector p. Now we have to extend line AB on the both side like this. And this extended line is called axial line. On the axial line, we take a point P. The distance between O and P is represented by small r. Now, first of all, we determine the net distance of this point from minus q and plus q. But before, we put a test charge on point P. And this test charge is represented by q naught. Now, we will determine the net distance from minus q and plus q, such as we see that in this figure, line OA and OP meets at point O. So, the net distance of minus q from this point will be add up as r plus L. Again, for the net distance of plus q to q naught, we see that OB is included in distance r. So, we have to subtract it OB from r, that is L from r. So, the net distance will become between BP is r minus L. Now, after determining the distance, we have to determine the intensities due to minus q and plus q at test charge q naught. So, first of all, we start from minus q. You know that minus q and it is by default plus q. So, force will act between these two charges attractive in nature. So, the direction of intensity towards left side like this, and it is represented by E1. Similarly, intensity is produced by plus q at this point towards right side, because this is plus and it is also by default plus. So, its experience a repulsive force. So, due to this, there is act intensity due to this E2. After determining the intensity at point P or Q naught, we have to determine its expression. Now, we have to determine the expression of the intensity E1 and E2 as. So, E1 is equal to 1 upon 4 pi epsilon naught capital K times Q over. So, E1 is due to minus Q, and the distance between A and P is R plus L. So, here we will write R plus A whole square, and it is represented by equation number 1. Similarly, the expression for intensity E2 will be 1 upon 4 pi epsilon naught capital K times Q over, and you see that for E2, the distance between B and P is R minus L. So, we have to put here R minus L the whole square, and it is represented by equation number 2. Now, next point is we have to determine first of all which intensity is greater. So, look at these two expression, we see that all the quantities are same except the distance. So, this distance is more with respect to this, and hence this intensity will be less with respect to this. So, E1 is less than E2. Now, we will have to determine the net intensity, that is E is equal to E2 minus E1. And now, we are represented on here at this point net intensity as E, and the direction of this intensity towards the direction of vector P. Now, substituting this expression in this E1 and E2, we get E is equal to 1 upon 4 pi epsilon naught capital K times Q over R minus L the whole square minus 1 upon 4 pi epsilon naught capital K times Q over R plus L the whole square. After writing this expression, this will become in this equation terms. So first of all, we have to look carefully these two terms and also look, is there any common factor between these two terms? Yes, there is a common factor, and the common factor will be 1 upon 4 pi epsilon naught capital K and Q, because these two uh, things has include in both the terms. So taking out it as common factor. So so Q upon 4 pi epsilon naught capital K, open curly bracket, 1 upon R minus L whole squared minus 1 upon R plus the whole squared, close curly bracket. In the next line, we'll have to taking out the LCM of the denominator and solving the numerator. We get Q upon 4 pi epsilon naught capital K the LCM will be R minus L the whole squared times R plus L the whole squared, and on the numerator we get R plus L the whole squared minus R minus L the whole squared, close curly bracket. In the next step, we will have to expanding these squares, and these two parentheses will have to compress only one curly bracket. So we get in the next step Q over 4 pi epsilon naught capital K open curly bracket, on expanding the squares of the numerator we get R square plus L square plus 2 RL minus R square plus L square plus 2 RL. This will become minus. And here on the denominator in the curly bracket, R minus L times R plus L whole square the curly bracket. And here will become close the box bracket, and here will also become open box bracket. Now look at this numerator. We see that here is R square, L square, and here is R square and L square. Both have the same magnitude but opposite nature, so they will be cancelled out. Like this, R square will be cancelled out with R minus R square, and plus L square will be cancelled out with minus L square. But here we see that two terms are left, plus 2RL and plus 2RL. These are the same but having the same nature, so they will be added up. But in the case of denominator, we see that here is R minus L, here is R plus L, all are the same but opposite in the sign. So this will become as a formula, and we will write here E is equal to Q over 4 pi epsilon naught capital K and 4RL upon R square minus L square the whole square. Again, we have to compare R and L. We know that this distance with respect to R, so this distance is extremely very small. So you can write it because L is very less than as compared to R. So L square can be neglected. Now our equation will become E is equal to Q over 4 pi epsilon naught capital K times 4 RL upon R raised to the power we see that in the numerator and denominator there is a common r. So r is power 4 will be cancelled out with r. So we get in the denominator r cubed, that is r to the power 3. We write in the next step 1 over 4 pi epsilon naught capital K times 4 QL over r cubed. In this expression, we see that we have QL, but we also know that the dipole moment is P is equal to 2QL. So can be established P on the denominator of this expression? Yes, we can establish this because for being a dipole moment, we have to 2QL. So here L, here Q. So we will factorize of 4 as 2 into 2. So we will get in the next step. So E is equal to 1 upon 4 pi epsilon naught capital K times 2 into 2QL over R cubed. And you see that here is 2QL. This 2QL will become P. So in the next step, we will write it 1 upon 4 pi epsilon naught capital K times 2P over R cubed. So it is our expression of the intensity of a dipole, which is placed in the dielectric medium because in the denominator there is a capital K, and this capital K is the value of dielectric constants. So if the dipole is placed in a vacuum, so the dielectric constant will become capital K1, capital K is equal to 1. So we write here, if dipole is placed in vacuum, then K is equal to 1. So this expression will be E is equal to 1 over 4 pi epsilon naught times 2p over r cubed. This is our expression of the intensity of a dipole in a vacuum. So friends, that's all for today's session. If this helped, please subscribe, share and like this video, and also comment your doubt. Take care and creating. Thanks for watching this video. Goodbye.